Okay, from yesterday we were looking at piecewise functions, and I left off. I don't think I got to show you this, but I wanted to just share with you how you can do this on Desmos. Okay, so here's how. I want to take a look up here. So if I want to graph, for example, this piecewise function, here's how you do it. First thing you do in Desmos, you have to use function notation. So f of x equals in Desmos. And then I'm going to open up a set of script brackets. And those are the ones, it's like to the right of the p, okay? First part is I'm going to do the top piece. And so notice how I do this. There's an order to this. It's kind of backwards. You enter the domain first. So I would say x is less than or equal to -2. And then I put a colon that's going to connect the domain with the function that goes with that domain. So domain first, then the function or the rule, the equation I'm using for that top piece, which is 2x. And that's going to graph the top piece. I have to put commas between each of the pieces. So then I would put a comma separating the top piece from the middle piece. And what's going to come next? In the middle piece, do you suppose? Okay, good. X is greater than -2 and less than 4. Got to put the domain for the middle piece. Then what comes next? Colon. Because I got the domain first, then the colon, and then I need what? Yeah, -1 minus x. Okay, what's next? Comma. Good, because I got to have another piece in there. Then what's next? What do you think? What's going to be next? Trey, what do you think? What's next? Bingo. X is greater than or equal to 4. Now what? What do you think? Colon. Then last part? -3. That's it. Okay, and if I do that, here's what I get. Okay? Okay, there's the piecewise function. All 3 pieces. Okay, it's unfortunately they're not color-coded or anything, but you get the 3 pieces. Okay, there's one other issue here though that's a little bit would be kind of helpful to be able to add to that. When I'm graphing these things, like yesterday when we did this in class, remember that we had, I got to go back quite a bit here, but we included the endpoints also. We wanted to know which endpoints got solid endpoints and which got open endpoints, right? Okay, well we can do something sort of like that on here. I'll show you a trick. So we know that the transitional x values, we're transitioning between pieces of the function at, let me scoot up, at -2 and +4, agreed? Everybody agree those are the x values where we're shifting between pieces? Okay? So those are the endpoints of some pieces. Here's what we could do to determine where we have closed endpoints. And we can see it from the inequality, but if you want to see it on the graph, all you have to do is go down here and just list the ordered pairs corresponding to the endpoints. Now notice how I did this. This is really important. So for the first ordered pair, in parentheses, because it's an ordered pair, I put -2 for the x value, comma, and then for the y value, I just put f of -2. So that means that Desmos is going to use this function that I built above to create that point on the graph. And I did a comma because I'm separating this point from the first from the second point. And then next to that, I've got another ordered pair where I've got the x value is 4, because that's my other transitional value for x. And the y value is f of 4. Okay, now watch what happens on here when I turn that on. And I can turn on the label and it'll actually give me the graphs. What do we notice there? It goes with the first and the second pieces. There are no closed endpoints on the middle piece. That makes sense, doesn't it? Because look, I'm not including any equal signs in the inequalities for the domain of the middle piece. So it would be getting open endpoints. The other ones are going to be the closed endpoints, and that's what we see. There are the closed endpoints. I would just make the assumption that anytime I don't see a closed endpoint, it's an open endpoint. Okay? Just a way you can use Desmos to fill in a little bit more information. Okay, give me a 1 to 5 on that. Okay? Okay, and you got to probably get a little practice with it. Okay? All right, so and I included a little, this little picture down there to summarize all that stuff. Okay, let's backtrack a little bit. I want to do this. I think this is the back side of the, what sheet is this? This is it the very last sheet or third page of those front and back pages or something like that? I don't know. It's on there. It's not the first page. It must be the second page. Okay, this is a special kind of piecewise function, the greatest integer function that we use quite a bit in math. We use it a lot in calculus. The symbol for it. The symbol is kind of this double struck bracket. Okay? And that's what we call the greatest integer function. Another really common name for it is the floor function. They mean the same thing. Most technology is going to use the word floor. Although the TI-89 or TI-84s, they use INT for greatest integer. So they're kind of an exception. The function on the TI-84 is INT, but as we're going to see on Desmos, it's floor. Okay? So what does this mean? The greatest integer function just means the greatest integer that's less than or equal to the input x. In other words, we're always just going to round down to the next lowest integer from whatever our input is. Okay, so let's just try a couple examples of this here, just so you get the hang of this. It's not hard to work with. So what about if f of x is the floor function of x, what is f of 7? If I input a 7, what's the output going to be? What's the greatest integer that's less than or equal to 7? Once again, the greatest integer that's less than or equal to 7. 7, there you go, okay. What's the greatest integer that's less than or equal to 2.3? 2. What's the greatest integer that's less than or equal to negative 4.8? Negative 5. You can kind of conceptualize this by, think about on the infinite real number line, x-axis, let's say, if we put a naught at every integer, it's like taking a bead and trying to slide the bead as far to the left as you can go until it hits a naught. Okay? What about something like this? How about this guy? We've got the new function here is the floor of x minus 5. Okay, so what would I get if I input a 9? I'm going to get 4, aren't I? I'm going to get the floor of 9 minus 5, which is the floor of 5, or sorry, which is floor of 4, which is 4. Okay, now what about b? What's the floor of 0.5 minus 5? What's the number inside the floor function there? Here's f of x. What's 0.5 minus 5? What's 0.5 minus 5? Negative 4.5. And what's the floor of negative 4.5? Negative 5. Okay, how about C? That's going to give us, here's f of x, right? So what's the floor of negative 8.1 minus 5? Okay, it's the floor of negative 13.1, which is what? Negative 14, right? Right? The greatest integer that's less than or equal to negative 13.1 is going to be negative 14. I'm sliding that bead to the left, right? I've got to drop down to the next lowest integer, furthest to the left on a number line. Does that make sense? Okay. All right. So then, what's this look like? Let's look at what a graph of the floor function looks like. So we know that if I'm inputting values, if I input 0, I get 0 back, don't I? Right? What if I input like 0.1? I'm going to get 0, 0.5, 0.6, 0.7, 0.8, 0.9. What's the floor of 0.99999? 0, right? It switches though when I input a 1. When I input a 1, all of a sudden now the floor function jumps up to 1. And it's going to stay there for all the inputs of x that are greater than 1 until I get to 2, and then it jumps up the step up to 2. And it's just going to have that same pattern forever. So it's like an infinite stairway. This is a type of step function is what we call this in math. Okay? Where it makes these sudden transitions. Okay? So what about something like this? Now we'll look at this in just a couple quick ways here. Let's do one of these, like making a t-table manually, and then I want to show you how to do these on Desmos. Super easy to do on Desmos. Okay, so what if we did something like, how about if we start at, let's start at 0. So if I input an x value of 0, what number ends up being inside the floor function? 4, and the floor of 4 is 4, okay? What if I input a number like 1? I get the floor of 1/2 times 1 plus 4. Okay, so that's the 4.5, right? The floor of 4.5, we'd round down to a 4. Okay, what about something like 1.99? Half of 1.99 is going to be something a little bit bigger or less than 1. Half of 1.99 is going to be greater than or less than 1. Slightly less than, right? Very close to 1, but slightly smaller. So I'm going to get something like a 4.99 something in there, right? Does that make sense? Inside the floor function, what's that round down to? Okay. When does it jump up to 5? At 2. Yeah. As soon as I put a 2 in, now I get the floor of 1 plus 4 is 5. The floor of 5 is 5. And it's going to stay that way all the way up to like 2.99, right? That's going to give me something very, very close to 6 in here, but it's going to be the floor of like 5.99 something. So I'm going to get back a 5. You can see the pattern then, can't you? Right? This thing's going to look like at 0, the output value is 4. So right there. Up to, when I get to 2, I'm going to have an open end point on my blue step and a closed end point on my green step. And so on. And I could just, I've got that same pattern, don't I? It's just going to go forever and ever. Okay? Okay? Give me 1 to 5. Is that making sense? Question? Okay, somebody else answer that. How come we've got open endpoints on the right of each step and closed endpoints on the left? Okay. Good. Okay, because the definition of the floor function is we're going to output all of the numbers that are less than or equal to the input function, right? So on this blue step, for example, as I get closer and closer to 2, as long as I don't equal 2 yet, then I haven't yet gotten to the next integer, and so I'm rounding down. But as soon as I get to 2, then I'm going to jump up a step because now there's no place to round down anymore. Okay? Why couldn't we, that's another question you guys can answer for me. Why couldn't these both be closed endpoints? What's the problem with that? Wouldn't be a function, right? Right, we can only, it'd fail the vertical line test then, wouldn't it? Okay? Does that help? Okay. What else? Any other questions? Okay. Let's look at how we can do this on Desmos. So that's it. In Desmos, we would just do f of x equals, and then we're literally going to type out the word floor. I think that must probably show up down here somewhere. If I go to functions, and maybe it's going to be under miscellaneous. Yeah, there it is. Floor. But, you know, it's a lot quicker just to type floor. So floor, and then in parentheses, we'd put everything that's inside the function. So 1/2 x plus 4. And notice we get the same thing when I type this in on Desmos that we got when we graphed it, okay, with the t-table. Okay, again though, it'd be nice to be able to see where the endpoints are, right? So I'm going to show you another trick on Desmos. Desmos is, I mean, it's really a pretty clever little program, and you want to get to use it, you get to know how to use it well. So I could go down, let's just start from scratch. I'm going to build a table. So I hit the plus sign, remember, to build a table, and we've done a bunch of this stuff before. Now in my table, I don't want this to be y1. I'm going to call this f of x1. Okay? And then look what it's going to do now. We want to go maybe by, it looks like all of the endpoints are on the even integers. Okay, so why don't I start down here at something like, let's say, -10. And then I'm going to go to -8, and now it's going to see the pattern, and I can just do that. It'll fill in the table for me. And then if I graph these, look what happens if I, well, they're graphed right now. See, look what it does. It graphs the endpoints, and we can see that the endpoints are at the left edge of each step. Okay? Give me 1 to 5 on that. And you kind of just have to get in there and play with it a little bit with Desmos. Okay, I'm going to make a little picture of that for you for the notes. Okay, there it is. I threw in here how you can do this stuff on the TI-84s as well, but I doubt you're going to do a lot of that. I think that's it. Yeah. So I threw a bunch of extra stuff in the notes. It gives you all the keystrokes to do this on a TI-84, and it gives you kind of some screenshots, but I'm sure you're going to do this on Desmos anyway. All right, so now you can go ahead and get started on the assignment. This is the new one, which is, I'll tell you here in a second. So this is 3.1 practice.